Physics is fascinating because of many reasons, of course, not least that it works. But one reason is certainly that it gives a touch of plausibility to ideas that otherwise seem like pure fiction. Strange objects that you think shouldn't exist. Wormholes, invisibility cloaks, or birds. But the physics idea that has captured imagination the most are probably parallel universes. The many worlds interpretation of quantum mechanics has it that anything which can happen does happen in another universe. Really. In this much asked for video, I want to explain how the many worlds interpretation works. Is it science? Does it solve any problems? And are the parallel universes real? That's what we'll talk about today. When you look around yourself, you see a lot of stuff that's somewhere in some particular place. Or if you're watching this in a pub, maybe stuff that's walking around on two legs. But legs or not, everything around you has very definite properties. It's not in two places at the same time or smeared out across the room. Or if it is, maybe you've had enough beer for tonight. If you look at very small particles, however, things are very different. Take, for example, our good old friend, the electron. An electron is described by a wave function, usually denoted with the Greek letter psi. But the wave function doesn't tell you where the electron is or where it's going. From the wave function, you just calculate the probability of what you'll find when you measure where the electron is or where it's going. For example, the wave function tells you the probability of finding the electron in a particular place. But before you measure it, it isn't in any particular place. It could be in several places, or indeed be smeared out across the room. According to standard quantum mechanics, often called the Copenhagen interpretation, nothing has definite properties until you measure it. Not just small particles, but also large objects. It's just that large objects, like that pint in front of you, are constantly being measured in some sense because light and air molecules ping off them. The Copenhagen interpretation does not explain just why some interactions result in measurements and others not. This is the measurement problem of quantum mechanics. What makes quantum mechanics so weird is this switch from a particle that's described by a wave function without definite properties to a particle that has definite properties, which you know because you just measured it. Say you take a quantum of light, a photon, and you send that through a beam splitter. No, we don't take our friend the electron. Friends don't let friends go through beam splitters. Because if you send a photon through a beam splitter, then its wave function says that the photon goes both ways. It's what's called a superposition of both possibilities. Let's say that each has a 50% probability, but once you measure the particle on the right side, you know it's not on the left side. This means you have to update the wave function. Since the wave function only tells you a probability, the outcome of a measurement can't be predicted with certainty. This is why quantum mechanics is not deterministic. This update of the wave function is sometimes also called the collapse or reduction of the wave function, and it's a key element of quantum mechanics. If you don't update the wave function, you'll get wrong probabilities. If you want to know, for example, what's the probability of measuring the particle on the left, given that it was measured on the right, the answer should be 0. But this only comes out correctly if you update the wave function. The update of the wave function is instantaneous. It happens at the same time everywhere and is the reason why quantum mechanics is non-local. This wave function update is what Einstein called a spooky action at a distance. I did an entire video previously about what this means, but here's the brief summary. Quantum mechanics in its standard version is non-local as a matter of fact. That's just a property of the theory. The key question is whether this non-locality is also a property of reality. Whether that's the case or not depends on whether you think quantum mechanics is fundamentally correct or just a description of an underlying reality. We still don't have an answer to that. If quantum mechanics is fundamentally correct, then the world is non-local, period. But if there's an underlying reality in which the outcome of a measurement was determined, we just didn't know of it, then this reality could well be local. This is called a hidden variables model. Think back to the example with the beam splitter. If there was an underlying reality, the photon went either left or right. You just didn't know what it did until you measured it. In this case, the wave function would just describe your incomplete knowledge. And while in this case the update of the knowledge is still non-local, that's not a problem, because the photon itself traveled entirely locally to the place where it's being measured. For this to work, however, you need something else, more variables that tell you where the photon really went. Since it's a rather persistent myth, let me add that hidden variables models have not been excluded by experiment. But it's somewhat off topic, and I explained all this already in a previous video. For today, the important point is just to understand the reason why quantum mechanics is non-local. The reason that quantum mechanics is non-local is a combination of A, the observational fact that a measurement outcome in one place tells you something about another measurement outcome in another place. If you measure the particle here, you now know you won't measure it there. Fact, not interpretation. And B, the absence of other variables in the theory that could have carried the information locally. This is why quantum mechanics is non-local, and this is also why hidden variables can restore locality. But this is not a video about hidden variables. The many worlds interpretation now is based on the idea that you can throw out the update of the wave function by reinterpreting what happens in a measurement. According to this interpretation, all outcomes of a measurement happen, each in its own universe. But we can only ever see the result in one universe, so for us it looks like the wave function collapses. Instead of the measurement update, in many worlds we have what's called a branching or splitting of worlds. This branching makes it impossible for one observer to see more than one outcome of a measurement. The major challenge for many worlds is to explain why the thing we call an observer does not itself branch with those worlds and therefore sees all the outcomes, but somehow randomly only experiences one of those worlds.